Okay, so the value of our sample mean, it says here, the value of the sample mean X bar we use to estimate the mean mu, and it's a single value, so we call that a point estimate of mu. What's often is more significant to us is to be able to come up with an interval, okay? An interval where we expect to find mu, an interval that we expect to find the mean, and that's called a confidence interval, all right? So keeping in mind that when we first looked at probability, we spoke about how mu minus 2 sigma, mu plus 2 sigma was approximately 95%, okay? Well, in actual fact, what we can show is with our normal distribution that it's not exactly 2 times the standard deviation, it's 1.96 times, okay? So a 95% confidence interval for the mean X bar of the distribution of the sample is given by X minus 1.96 times the standard deviation, which is sigma on root n, sigma plus 1.96 times sigma on root n. All right, so I think the easiest way, if we have a bit of a look at an example and what does the answer give us? All right, so if I want to find a 95% confidence interval for the mean IQ of students, we're going to take a sample of 100 students and find the sample mean, or we found the sample mean to be 108.6. Okay, I want a 95% confidence interval. So what we're saying is, okay, so the sample mean was 108.6 for this particular population sample, minus 1.96 times sigma on root n, which is 15 over root 100, which is 1.5, 108.6 plus 1.96 times sigma on root n, which is 1.5, gives me a value of 105.66 to 111.34. Okay, now what that tells me, here we go, the interpretation is good. So the correct interpretation of this interval, we expect 95% of such intervals to contain the population mean. Okay, so I'll go on. Whether or not the particular confidence interval obtained contains the population mean is not generally known. So what we're saying is that if we do 100 samples, okay, if we sample, if we get 100 students and work out the average population, the average IQ of each of those 100 samples, so 100 lots of 100, okay, I would expect 95% of their average IQ scores to be within that interval. Okay, so if I sample one, I'd expect 95 of them to have an average IQ of somewhere between 105.66 and 111.34. All right, we can get this on our CAS by selecting the Z interval on our confidence intervals in our calculator. And that's something we might show specifically in class. But you can see my 105.6 into 111.54, where we have to be able to type in the sample mean, the number of samples, or the size of the sample, and the standard deviation of the distribution. All right, so that's what that's saying. All right, now if I want to increase the confidence interval or increase the accuracy of that confidence interval, let's take a bigger sample. What if we do exactly the same thing, except I take an average of 400 students? A sample of 400. So the mean is still 108.6. My standard deviation is now 15 over root 400, which is 15 over 20, so 0.75. So now, 108.6 minus 1.96 times the standard deviation, 0.75, 108.6 plus 1.96 times standard deviation, 0.75, gives me an interval of, what does that give me? 107.3 to 110.2. So you notice it's a lot smaller. All right, so now what I'm saying, if I take a sample with 400 students, in reality, I would expect 95% of the samples that I take will be somewhere between 107 to 110. All right, a little bit smaller than the 105 to 111. And that's because I've taken a sample of 400 to begin with, so it's a more reliable sample. Okay, if I take a sample size of 2, well, clearly there's a lot of variability in that. And so my confidence interval would be much bigger. All right. So in short, the greater the sample, the smaller the confidence interval. Okay. And again, you can see the values there in our calculator CAS. Now, what sort of error are we expecting? What is the margin of error of a confidence interval? And the margin of error is just the distance between the sample estimate and the what? All right, so it's come down, and the endpoints of the interval. So in other words, it's that 1.96 plus times sigma on root n, because we start at the middle value and then we add a bit and we subtract a bit. So this is my error. So sometimes we want to make that error fit to be within a certain size. So sometimes questions pop up with, if I rearrange this to solve for n, okay, I can tell you how many, how big your sample needs to be to ensure the error is within a certain range, or the error is under a certain size. So if we've got the same scenario, except this time I want the margin of error to be 1.5 points. So in other words, it's going to be the average value, the mean value plus 1.5 or minus 1.5. So the easiest way is just have the rule written down. You can rearrange it from the formula which is given on our formula sheet. But if I want to work out n, 1.96 times 15 over 1.5 is 384.16. Remember, n is a sample. How many in the sample? So it's either 384 or 385. And to make sure it's under what we need to make the sample at 385. So we don't necessarily round to the nearest whole number. We round to the nearest correct number, which in this case happens to be increasing. And it will typically be increasing. All right. We can change the confidence interval. All right. So I've got 1.96 there for K, and a 1.96 times the number of 1.96 times the standard deviation gives me a 95% confidence interval. From our knowledge from our inverse normal, okay, they're the different key values there. So if I want 95% of my data to be within, I use 1.644. Now, that's, sorry, 90% of my data is 0.95, because what we're saying is, if we just do a quick graph sketch, what we're saying is that's 95% there, which means I have 2.5% either side, yeah? And that's where the 2.5% is 0.025. If I want to make this if I've got 0.95, that makes that there 5%, which means that down here has to be 5%. So in actual fact, that one there gives me a 90% confidence interval. So that's my 90% confidence interval, 95% confidence interval, 99% confidence interval. 2.58, 1.96, 1.64. Okay, so they're the K values that we use. So if we want to get a 90, 95, and 99 and compare them, 1.65 times the standard deviations gives me that value there. So that's my 90% confidence interval. 2.58 times the standard deviations gives me a 99% confidence interval, and we had our 95% confidence interval previously. So clearly you can see between the 90 and the 99, what we're saying is that 99% of my average IQs from my samples will fit within this interval between 104 and 112. Okay, so that's going to be 99% of my observations. All right. If I only want 90% of the observations, or 90% likelihood, 106 to 111. Okay, so that's my confidence interval. And so that often depends. Okay, this ties in a little bit with our method stuff using our inverse normal. All right, but typically they're our standards, 90, 95, or 99%. And 95% confidence interval is the one we typically use.